Satellite imagery can allow you to track the forcing mechanism for your severe weather event. Severe storms need a mechanism for forcing for ascent in order to initiate. The atmosphere can be as unstable as it wants, but if there isn't some sort of mechanism to push that air near the surface up into the vertical to tap into that unstable environment, storms are not going to be able to initiate. In most cases, the forcing mechanism for your severe weather event is going to be a trough, in particular a shortwave trough. In the previous episode, we talked about how to use water vapor satellite imagery in order to identify and track troughs and ridges. You can also use visible and infrared satellite imagery to track the arrival of the shortwave. Oftentimes, shortwaves will be denoted by a band of high clouds, typically cirrus clouds, and when the leading edge of that band of high clouds overspreads your area of interest, storms will start to initiate or intensify. Here's a good example of that. Notice this batch of high clouds emanating out of West Texas. That is a batch of cirrus clouds denoting the shortwave. We can see that they're moving from west-southwest to east-northeast, matching the upper-level winds. Therefore, we know it's likely a shortwave trough that is being demarcated by these high clouds. And as the leading edge of this batch of cirrus clouds start to overspread the target area, which on this particular day, in this case, it was kind of the western Oklahoma to northwest Texas area. Once that leading edge of that batch of high clouds, i.e. the shortwave, starts to overspread the area, you'll notice that the intensity and coverage of the storm start to increase rapidly, especially across western Oklahoma. You see the leading edge start to impinge upon that area, and thunderstorms start to really intensify over that region.
The Chaser Academy is the best deal in storm chasing. Click the join button below this video and find out why.
Switching over to visible satellite imagery, you can see the wispy clouds here. That is that band of high clouds, and as they start to overspread that area of western Oklahoma, those storms start to really intensify there into full-fledged thunderstorms. Now, not all shortwaves are going to be demarcated by these bands of high cirrus clouds, but oftentimes they are, and when they are, satellite is a very good tool to use to track the progression of the shortwave. Visible satellite is an excellent tool to use to identify outflow boundaries. Outflow boundaries are demarcated on visible satellite imagery as very fine lines of clouds, usually small cumulus clouds. And outflow boundaries occur when a storm or storm complex emits a lot of cold air. And the interface between the cold air that the storm complex emits and the warm air that was already in the environment, that is your outflow boundary. Usually there is a wind shift along that boundary as well. Winds to the north of the boundary might be out of the north, pushing out cold air from the storm complex, while winds on the warm side of the boundary might be out of the south or southeast, for example. The winds are coming together along the boundary, which forces air to rise, so you get small little bands of cumulus right along that interface between the cold air and the warm air and where those winds come together. Outflow boundaries are important in severe weather forecasting and nowcasting for a couple of reasons. Number one, because winds are converging a bit more strongly along the boundary compared to elsewhere, you can have actually a better chance of just initiating storms along the boundary. And number two, supercells that can anchor to and track along an outflow boundary may have increased chances of producing tornadoes because outflow boundaries have enhanced low-level wind shear and vorticity, a fancy word for spin, along them. So supercells can tap into that enhanced low-level shear and can ingest the vorticity along the boundary to have increased chances of producing tornadoes compared to storms that are not anchored to the outflow boundary. Now, not all outflow boundaries are optimal for increasing tornado potential with storms that track along them. You want your boundary to be slow-moving or stationary. This gives the storm a better chance of actually latching onto and tracking along the boundary. And you want your boundary to be oriented parallel to storm motion. Again, this allows the storm to actually track along the length of the boundary, tapping into that increased low-level shear and vorticity to increase tornado potential. Fast-moving or surging boundaries are not optimal. They tend to undercut any storms that fire along them. The storms immediately go to the cool side of the boundary and therefore become what we call elevated above the low-level, stable, cool air mass. Elevated storms are generally unable to produce tornadoes. Slow-moving boundaries tend to happen when your temperature gradient across the boundary is fairly low, meaning there's not a big difference between the temperatures on the cool side of the boundary and the warm side. Usually when there is a big temperature gradient between the two sides of the boundary, that cold air is going to win out and really push that boundary and allow it to surge, which again is unfavorable for storms latching onto the actual boundary. Also, if you have a lot of persistent regenerative convection on the cool side of the boundary, that's going to also allow the boundary to surge quite a bit. Those storms are going to continue to produce outflow, which adds to the boundary and allows it to continue to surge. But if that convection tends to dissipate with time, that is going to allow the boundary to eventually slow down or even stall, because that outflow source that continues to push the boundary along is no longer there. So even if you have a boundary that is being forced by a convective complex, if that complex tends to weaken with time or dissipates altogether, that's a good sign for your boundary eventually stalling at some point later on. Let's take a look at this example here. So here is our boundary clearly defined by this band of clouds emanating from a pretty stout complex of convection, much of which still ongoing out here across the North Texas vicinity. But notice how this portion of the boundary was pretty free and clear of convection on its cool side. So that might start to give you a little bit of a hint that that portion of the boundary may eventually stall out. This portion here to the east, where the convection was continuing to fire to its north, that was likely going to continue to sag. But because we had a lack of convection on the cool side of the boundary farther west, and also the fact that we had clear skies both on the north and south of the boundary, leading to a decreased temperature gradient from the cool side to the warm side of the boundary, as both sides of the boundary were subjected to strong surface heating. That would mean that there's mounting evidence that that portion of the boundary might stall out a little bit later. And sure enough, you see still a little bit of south movement there, but eventually we go into the afternoon here, and that boundary kind of stalls out, really slow moving right in this area here. And given that storm motion was to the east or east-southeast, that was going to parallel any supercells motion that tried to track near the boundary. And sure enough, supercells went up along the boundary and tracked right along it, and that supercell there became tornadic as it tapped into that enhanced low-level shear environment along the boundary. Now, a couple of notes. Not all boundaries will show up on visible satellite imagery, and some boundaries that become more diffuse with time may actually disappear from visible satellite imagery going into the afternoon of a severe weather event. Neither of these mean that the boundary is not there or has dissipated completely. Always use multiple factors to confirm the location of a boundary. If you're unsure of whether a fine line on visible satellite imagery is a boundary, or maybe the boundary is really subtle and you can't really see it on visible satellite imagery, make sure to look at other factors like radar, surface observations, etc. to confirm the location of the boundary. Another feature you might often see in visible satellite imagery in the lead up to storm initiation, and sometimes during and just after storm initiation, are cloud streets. Cloud streets are these linear bands of clouds that you see in the image right here. These are the result of horizontal convective rolls, or HCRs. Horizontal convective rolls are adjacent vortices oriented horizontally that rotate opposite one another, and where the winds converge in between rolls, you get these cloud streets where the air is forced upward. Now, these cloud streets are indicative of lingering stability in the environment. If you see an area with these cloud streets in it on satellite, that tends to mean that the area has not destabilized fully yet. There's a little bit of stability left in the low-level environment. Of course, we want an environment that's fully destabilized in order to get the most robust storms. So if you see storms that are moving into an area where these convective rolls are prevalent, that usually is a sign that the storms might struggle with low-level stability issues and may be elevated. Again, that means that it's elevated above a stable layer near the surface, which is unfavorable for tornadic activity. Oftentimes you will see these cloud streets dissipate as surface heating continues and the further you get into the afternoon, which signifies that the atmosphere is becoming more and more unstable. So the typical progression you might see on visible satellite imagery in the lead up to convective initiation starts off with a cumulus field, which is just an area where cumulus clouds start to develop. There'll be these kind of fair weather, small cumulus clouds, and the area can be larger than this one you see here. It can be smaller. It can be just a few cumulus clouds in a very localized area, or it can also include some of those horizontal convective rolls or cloud streets we just talked about. But overall, the first step toward storm initiation is for a cumulus field to develop. Then, as the atmosphere becomes more and more primed for storm initiation, some of those cumulus will become what we call agitated. Notice in this area here, the cumulus have become a little bit better defined, a little bit more vertical in nature, going from those small fair weather type cumulus into more cumulus congestus, which is that real cauliflower looking cumulus cloud with vertical extent. Not a full-fledged cumulonimbus cloud or thunderhead, but definitely well on its way. So these are agitated cumulus. It's a sign that the environment is becoming more and more favorable for storm initiation. And then once the atmosphere is fully destabilized and the forcing mechanism in question arrives, then you'll see full-fledged convective initiation. Those clouds will become more and more agitated until they become full-fledged thunderstorms or cumulonimbus clouds, as you see here. Now, before that happens, sometimes you will start to get actual cumulonimbus clouds to develop, but the atmosphere might still not be ready for full-fledged, persistent, sustained thunderstorm development. In that case, you might see what's called an orphan anvil. So watch this cumulus congestus down here. It starts to develop into a full-fledged cumulonimbus cloud, but then it dies off, leaving just the anvil in its wake. This is called an orphan anvil. What happens is the environment may be a little bit too stable still, a little bit capped, and so thunderstorms try to go up. Maybe the forcing mechanism has arrived, but maybe it's not quite strong enough to really push those updrafts through the capping inversion. So the storms will try to become full-fledged thunderstorms, but then the updraft dies off, leaving just the anvil in its wake, which is an orphan anvil. So this is a sign that your atmosphere might not quite be ready for storm initiation, but once it does, you'll see those agitated cumulus go from that agitated phase right into the thunderstorm phase when you have sustained thunderstorm development and cumulonimbus clouds, as you see here. And here's another example. We start off the day with quite a bit of thick stratus across the area of interest, and then off to the west we eventually get a cumulus field to develop there in the Texas Panhandle area. The cumulus persist for quite a while. They get a little bit agitated right in there, and then eventually we get full-fledged thunderstorm development as we became fully destabilized in the afternoon. Another tool you can use to monitor for storm initiation is the day cloud phase product. This is not a single band or channel. Instead, it uses a combination of multiple bands to come up with its output. What the day cloud phase product does is, starting with a combination of information from band 2, which is the visible red band, band 5, which is the snow and ice near infrared band, and band 13, which is the clean long-wave infrared band. It uses information from all of these bands to come up with differences in the reflectance of clouds. Reflectance is basically just a measure of how much light clouds are reflecting. This allows us to see increased contrast between clouds of different phases, basically clouds that are made of water versus clouds that are made of ice. As we've talked about before, clouds that grow higher and higher into the atmosphere get colder and colder, therefore fostering more ice production. So taller clouds are going to have more ice crystals than clouds that are much lower in height. So that allows us to see where cumulus clouds are becoming more robust. Now, this is the full breakdown of all the color schemes in the day cloud phase product, but we really want to be focusing on the blues and greens and yellows. Cumulus clouds that are transitioning from lighter shades of blue and green to bolder shades of green and even yellow and orange indicate that those cumulus clouds are undergoing vertical development and seeing an increased presence of ice within them, which of course is a hallmark of strong updrafts and robust storms. Here is an example. Notice how these clouds at the top left corner of the screen are comprised of mostly light blues and greens, which means that they are full of mostly water droplets. This suggests that they are not all that tall, not all that robust. But Watch as they move off to the east. They take on a lot more of those greens, yellows, and oranges, indicating that they are now quite full of ice crystals. That means that they are a lot taller, a lot more robust in nature. Here's another example from this same loop. Keep your eye on these developing cumulus here in the pink circle. Watch as initially they take on a lot more of those greens and blues, indicating that they are lower level clouds, not all that robust. But this one up here starts to take on a little bit more of those yellows and oranges, meaning that that is a little bit more of a robust updraft. So this is a good tool to use to maybe, if, in a situation where you have a lot of updrafts that are trying to initiate, this is a good tool to help you see which ones are becoming more robust more quickly. The ones that have more of those yellows and orange colors, those are going to be your more robust updrafts, more ice crystals in those updrafts, meaning that they're taller and more intense. As its name suggests, the day cloud phase product can only be used during the daytime because it's drawing in information from band 2, which is the visible satellite band. It cannot be used at night. If you try to use the day cloud phase product at night or when the sun angle is low, so right before sunset, for example, your output is going to be artificially tinted red, which is not going to allow you to differentiate between different cloud phases.
Remember to check out those links in the description below, and then watch another video.